A little about me. For my daily work, I work for a Dutch government agency in a position as a data scientist. This position just gives me the means to do coding a lot without the bureaucracy of a government IT department. I have a PhD in physics, and you see in the data science community that there are actually a lot of physics people over there, so that's not a problem. My position also gives me the opportunity, the freedom to pursue the interesting technologies that I like graph analytics and data fusion, and at the same time I can be of some use to my organization. In my work, I'm not bound to any technology, whether proprietary or free and open source. The only emotional attachments that I could have is to Apache TinkerPop and JavaScript because of the work I did for that. So, differentiated access control to graph data. We'll first explore a little bit the issue so that we all see it as the same way. Then I'll explore 3 directions in how to tackle this issue. And of course, one of the 3 I've worked out, and I'll demonstrate that in a notebook demo. So, first, why would we need access control in the graph data, and what are the tricky points of that? Normally, when you ingest data into a graph, you have data from multiple data sources. So in this diagram, for example, you could have data from some application of a business department, let's say buying history. You could have some data from a finance department, and you could also have some marketing research team that have downloaded a lot of Facebook data, and they also want to include it in the graph. And now, of course, when you have so many data sources, you have to deal with privacy laws, and often there are also corporate policies in which data you want to combine, yes or no. So that introduces the access control. So one example here, just say that the business department wanted to do some recommendations to customers. But there are corporate policies that they cannot use the social media data, or they can also not use the exact location data of customers for the recommendations, because the business thinks that customers would feel uneasy if they see that the address data or the Facebook data is actually used for the recommendations. They would soon find out. So in this diagram we see, for example, that this location data only comes from the finance department, and we can assume that the customers and the products are part in all 3 of the data sets. We can then zoom in just one issue of graph traversals and access control. Let's say that we have 2 data stores with persons in it, and from both data stores we get edges between the persons, for example, if they know each other or so. When then some user has only access to the edges of store 1, this person cannot do, this person, when it does a graph query finding relations of person 1, it shouldn't get back this person 4, because it is not allowed to visit this, to see this relation. So now we have seen what this access control in graph data is about, and when you think about how you could address this issue, there are a few ways you could go. First one is just perfectly isolate graphs. That means build separate graphs for each user group that you have. But of course, we will see that in a minute, that has some problems with it. Second possibility would to do this in your graph store, to build access control mechanisms into your graph store. And the third way we will explore is to just do the filtering in your application itself and see how that performs. So first, let's see what happens when you have just make separate graphs for each user group that you have. So I've drawn here a few criteria. We have here the case for one graph for all user groups, and we have here the column for the separate graphs. The first thing that hits you regarding scalability is the number of management processes that you have. Just maintaining a graph for each user group will be very expensive from a management perspective, because you have a lot of processes that go wrong and you have to keep track of all of them. So that's not nice. Second important thing is the available cache memory in your graph database. Of course, the performance of a graph database is greatly enhanced by cache memory, because often visited nodes will be served from memory. When you have just one graph, then you can apply all the cache memory to the single graph. But if you have a graph for each user group, then of course the same often visited node will be as often in your memory copies of the data as the number of user groups that you have. So this will just dividing the cache memory between graphs will hit your performance. We will also see this with usage of CPU cycles. Of course, when you do some authorization processing, this will require more CPU cycles. But also, when you have separate graphs per user group, this means that all the graph data you have to fetch from disk and send over the network separately for each user group. This also requires CPU cycles. So here we see that in both cases the performance or the required resources will be hit in some way. Of course, disk and network I told about. Maybe there is one advantage of having separate graphs per user group. That is the case that your graph database will get corrupted in some way. Then of course there is just one single user group that is affected. And scalability we talked about. So all in all, when we look at this table, that we see that if you build separate graphs per user group, that is very painful. So we wouldn't really like to do that, unless maybe you have just 3 user groups or so. The second direction, let's see whether we can do something inside the graph database itself. And for that we have to see how a graph database stores its data. This picture is taken from the Janus graph documentation, but from a high-level viewpoint, the same holds for Neo4j. Because graphs in general are very sparse, you have to store graphs in an adjacency format. So basically for each vertex in your graph, you have a row in your database, and in this row there are cells that contain properties of your vertex, and it contains the edges, the adjacencies of the vertex. And as we have seen before, we can also have access control rules on the edges itself. So this means that you have access control information required on this edge itself. So you already see that you end up with cell level security, and in some way the graph database and the access control information you would have to store in your data format somehow. When you look up the way how Janus Graph or Neo4j stores its data, you see that at this stage is not catered for. And as I see it, it wouldn't be very easy to enhance it into it. At least it wouldn't be a 1-week project or so. It would be a lot of work. So I didn't pursue this way of enhancing the graph database with access control. Fine. Yes. So then the third direction I would like to explore, and that is just to do the filtering inside the application. So what we do then is that we just use the regular data format of the graph database, and we store authorization properties into the vertices and the edges of the graph. So each vertex, each edge would get an authorization property, and in the most broadest sense it would be just an array of values. And in this example I took strings because they are human readable, so easy to understand. And of course in the graph itself you wouldn't want this list not very long, because all the values have to be stored. On the other hand, at the user side, you can assign authorizations to the user, and this can be a very long list if necessary, if you have a lot of sources with a lot of authorization levels. For example, here for the business source, we have authorization level 1, 2 and 3, and there are always all kinds of ways you could encode your own authorization rules. So this is a high-level view or architecture how you could put this into your application. We assume at the bottom that there is an external graph database where you get the graph data from. And we assume that the filtering that we do on the vertices and edges that we do in the context of a secure endpoint, which is this API, and the overall graph application business logic would be at an upper tier. So this part here, the filtering and the restriction, it would filter all the data that comes back from the graph database, and it will also restrict the overall API of the graph database. And why that is, we will see in a minute. And if you use this kind of build-up of your application, then you do the filtering and the restriction, so the security part of your application, you do it at one part, so you have a proper separation of concerns. And as a result, it is less likely that you will make any errors in your code to send the wrong data to some user. You only need to have this part absolutely right. And this also makes graph applications easier to audit, because normally this part would have very few changes, while when you extend your application and you will add more graph queries, this part will be much more valuable. So this approach, this seems feasible, but of course to check it whether it's really feasible, you have to do the experiment. So that's what I did, and I'm going to show you that in a minute in a demo notebook. Just check the time. Yes. First, a little bit about, I will do this for Apache TinkerPop, and it also applies to Janus Graph. How many of you know Apache TinkerPop or the Grammarly query language? Just a few people, okay, no problem. When you in general look at the graph database, of course there will be some instance of a graph object where your basic API calls start. So when you use basic TinkerPop, it would be a so-called Tinker graph, and when you use Janus graph, then it would be the standard Janus graph object. From this graph instance, you can then instantiate a graph traversal source, and that one, when you issue a query, it instantiates a so-called default graph traversal. There can also be nested queries, which TinkerPop calls an anonymous graph traversal. And we also see that there are some other types of traversal which implement the same graph traversal interface. And this interface also has a part of the Gremlin language, or DSL. So what we do to have access control into this, those four classes and interfaces make up the Gremlin query language. And this is the Java Gremlin DSL. What we have to do is just slightly extend those four classes and interfaces. So then we get an authorized Java Gremlin DSL on top of the existing TinkerPop APIs. And this does then two things. It filters the data that comes back from the graph database, and it restricts the API, because the API gives you all kinds of opportunities to circumvent the filtering. And while doing this, you see that it is more or less, it is very straightforward. There are only a few cases where it gets tricky, and you need to apply so-called stack inspection. So you have to see who calls a certain API call, and based on who calls it, you block it or you block it not. You don't block it. And of course, this is very fragile, because now the additional APIs that you make do not just depend on the public APIs, but they depend on the actual implementation of these APIs. So in future versions of TinkerPop, this might just not work anymore, and you have to repair this for any version upgrade. So how do the traversals, the graph Gremlin queries look like, with or without this filtering? We have here a very simple traversal where we look for the friends of Mathilde that live in Brussels. And you see, while you traverse the graph with out, in steps, at each step when you go in the graph, you have to filter the user authorizations against the authorization property of the vertex or the edge. So this becomes very tedious, and it is also error prone, of course. And it is also possible to obfuscate the code so that some filterings maybe are not visible anymore. When you apply the authorized traversal source, so the extensions that I made, you only have to provide the user authorizations at the start of the traversal, and when instantiating the traversal object, you have to provide the proper class to it. And after that, the traversal looks like you would have normally in Gremlin. All the code for this is available from GitHub, and also the demo I will move into is also part of this repository. Okay, let's see. I'll keep this graph at hand because we will probably need it at the demo. This is how the demo looks like. You see that there is only a single jar that is added to the class path, which adds the classes of the authorized traversal source. And of course, I pre-downloaded some jars from the TinkerPop libraries. This is just some code to build the demo graph. So you see here some add vertices. Sorry. And here are some add edges. And here we have the unrestricted traversal source and the authorized traversal source, which we will use further on in the demo. And here's the picture again that is built from this graph. So again, normal operation. We will try here to get all the vertices from the graph and their names when we provide a user authorization of BIS3. So we can just see in the graph which vertices have the authorization of BIS3, and it's only P0 and V1. So let's run it. And indeed, on the unrestricted, we get all 5 vertices, and the authorized, we only get the ones with the proper authorization. Of course, we can do the same when we start from a single vertex, when we start from vertex with the name P1, and just do one out step. Here we'll do the example that we provide 2 authorizations, fin2 and fin3. We start here, and we provide authorizations fin3, so we can go here, okay, fin3, okay, fin2 also provided, but here bis3 is not provided. So when we run this, indeed we only get this second vertex. Okay, so this is again the normal operation. Now we come, so this is the filtering part of the API. Now we come to the blocking part of the API, because the normal TinkerPop APIs have a lot of methods that allow you to circumvent this filtering. So when we want to have the security part as a single concern at one place, we want to block those methods so that we're sure that the unauthorized data doesn't wander around in our code. So here's one example. First, let's see what happens when we do not provide user authorizations. Now that's very dull, it just throws an exception that you should call with authorization first. Of course, you could also try to do it 2 times, and the second time add more authorizations. People try things, and also here you get an exception that you can only call it once. So the object, the authorized traversal source, keeps track of how many times this with authorization is called. Then what you have to know is that the user authorizations that you apply to your query that is stored inside the traversal, that is just a property user authorization. You can even show it with a Gremlin query. Cap is a Gremlin step to output any side effects that you have stored in your query. So you see here indeed we have provided this bis3 authorization. So one thing we could try to circumvent the filtering is just somewhere in our code use some other part of the API called with side effect, and just try to override this user authorization property that we have filled with the with authorization call. Now, we can also try this, and we have seen this query before. That was the first one that you tried. So the P0 and the V1 result is what we really expect for the bis3 of user authorization. So apparently this call here doesn't, the with side effect call doesn't raise an exception, but it is ignored anyway. So it doesn't hurt us. Let me see how far I am in my time. Still okay. Here we have another way, other method from the Gremlin language to try to manipulate this user authorization value that determines our data filtering. That is the so-called store, or an alternative, the aggregate step. So we just try to inject another value for the authorization in this user authorization property. So also try to run that, and then we see that actually this user authorization property inside the traversal is an unmodifiable list, and the step tries to store it therein, but it raises an exception. So that's good. And here's another one that we can try. let's see what happens here. The TinkerPop APIs also have a few very low-level steps to make traversals. These are called the map, flat map, and filter steps. And into these steps, you can also provide with a function that gets access to the so-called traverser objects. And traverser objects, that are the objects that really go through the traversal and keep all the data that are necessary during a pass through the graph, so that at the end you can get the right output. And also these traversers store this user authorization value. And it turns out that when you get access to the traversers, you can really modify this user authorization value. So all these functions that get access to the traversers, they are blocked in the authorized API. So indeed, when we try to do that, it just the API raises an exception and says that the method is not available. There's another way to circumvent the filtering that we have blocked in the API, and that is just getting access to the graph instance itself. There is a very simple step for that, get graph, as you say. So once you have access to the graph, you can just get a new traversal source and get all the vertices that you want. So this was also blocked when you try to do this. You get again method not available. There is another way to get access to the graph instance, and that is by reflection in the Java language. So if you do it in this way, I've made an example. You can just get access to the demo graph instance, and when you have that, you can do the normal traversal. So when you see that, you can just get all the vertices of the graph. So when you really want to be sure that your authorized traversal source works as it does, and that not somewhere else in your code the graph instance is exact anyway, you have to set up a policy for your JVM security manager, so that this is not possible. I have one final example. That is about nested queries. Of course, you have to check when you do nested queries whether or not in the nested query the full graph is accessible anyway. So here's just one example how you could do. Here all the vertices of the graph are mapped just again to all the vertices of the graph. And this mapping is done every time for a single vertex. So here you have to fold the results of the full graph vertices so that you keep a single value again. And then here you unfold them, deduct them, and you get the values. And when you run this, we see again that we get the values that we expected. This is the same query that we did at the beginning. Just look at the vertices that have the BIS3 user authorization. So what we see here is that the nested query inherits the user authorizations of its parent. So that is how we want it. And of course, in the classes that I showed in the class diagram, the class for the anonymous traversal was changed in the same way as the other classes. And you can do the same way, the same when you do a nested query that has edges as a result. And also here you get the results you expect. We can check that. What do we here? We start from a vertex with the name v1, and we see which in edges it has. So we can see it in the figure. Here is the v1 vertex. It has two in edges, one with the bis3 authorization and one with the fin3. We only provide the bis3 authorization, so we only get one in edge out. Okay, that's the end of the demo. Yeah. So, let's wrap up all things. I hope I have convinced you that giving proper attention to access control in graphs can be very useful, even necessary when you use it in a corporate environment. And you see also, as already you said in the introduction, there's a lot to it and it's not easy to achieve. We have seen that if you use separate graphs per user group, that's a viable option, but it has severe penalties in terms of management processes that you have to do and also performance of your graph. We have also seen that cell level security, so integrated in your graph database itself, seems rather tricky to do this. At least it would be a large job. And as a fourth issue, we have seen that you can do it in the graph. This is feasible also regarding performance. Actually, performance of graph databases is often the fetching of data of vertices from disk and getting it over the network and do some additional filtering in the application is not actually a very lot of work to do. So you do not see this back in your performance. We have tried this with very large graphs of tens of millions of vertices. So doing it in the application is feasible, but still it is fragile because of the stack inspections, and also because these public APIs of the graph databases are so vast and they are really not designed for this kind of applications. You can only do this in the context of a secure endpoint. So you cannot give end users access to this authorized reversal source. Okay, I hope you enjoyed.
Any questions?
Possible to override the graph interface itself so that you dealt with the four classes that basically talk to the graph.
Mm-hmm.
If you override, if you take the wrap around the graph effectively, dynamic proxy to talk to the graph to do the filtering, would that have been possible?
Yeah. Yeah, it was very hard for me to understand.
Would it have been possible, instead of doing the four classes, to do just
Okay, yes. Yes, the question is rather providing four APIs, just provide a single API. Yeah, that would just basically an empty API because you have to build the four, and what's get left you can wrap up in one overall API, but it would just be forwarding, so I didn't see that as useful.
I wondered if you were expecting using the framework, is there a method that can show a given client that they haven't got complete data back so they're aware?
It's very hard to hear.
So the question was, if you have this framework, is it possible to show a client that they haven't got the full data back, but they have got a restricted setback of data, so that they're aware they're not seeing the full or the full result?
Yeah, I think you just would have to write test cases for that. What it's really to audit the code that you have that becomes much easier because there's only one entrance into the graph data, so you can just Control F for that. Yeah.
Okay, cool. I have a question. There are also kind of higher level ways of doing that, where you could say, okay, I put the security constraints on a label or relationship type or something like that.
Mhm.
Have you considered that as well, that you kind of pull up the level of granularity to an kind of part of the graph metadata structure? You say, okay, these people can't see these labels, or they can't see these kind of relationship types, and not have to
I
fine-grained.
didn't need that for my use case, but of course you see that for other big data stores, that you have ACLs as a kind of predicates, and I have just one predicate on my user authorization property. But of course you could implement other predicates as well. Yeah, sure.
Yeah. When you tested this on the large multi-million node and relationship graphs,
Yes.
what kind of complexity of the security rules did you have? Was it kind of a lot of user with a lot of different, or a lot of different?
Yeah, it's just these filter steps. So every vertex that you get another filter step. But at least for the Janus Graph database that I use, performance is mostly limited, but by how fast you get a vertex row back. And in this vertex row, you have all the data, so all the edges. And after that, once you get the data, it's a very fast operation to do all the filter steps.
Okay.
So that doesn't hit your performance.
Cool.